Hello, mathophiles. This episode of Adventures in Algebra, we are going to study the general linear group. And we're going to start the process of showing that it is a group. This is going to be a video in two parts. Now, of course, it's not clear what this means right now, but it's the set of 2 by 2 matrices with non-zero determinant. So, quite literally, GL2R is the set of 2 by 2 matrices, so A, B, C, D. These are real numbers, and our one restriction is that the determinant is non-zero. And for 2 by 2 matrices, the determinant is just AD minus BC. So product of the diagonal entries minus the product of the off-diagonal entries. And it is worth noting that there's a notion of determinant for arbitrary n by n matrices, and this is not the formula in the general case. So just pointing that out, because you can also prove that arbitrary n by n matrices with non-zero determinant form a group. Now, to make some of the notation easier for a lot of the proofs, for a matrix A, we're going to write it in this form. A sub 1, 1, A sub 1, 2, A sub 2, 1, A sub 2, 2. You might remember this from linear algebra. A sub ij is the entry in the ith row and jth column. As this is just part of that notation, just in the special case of 2 by 2 matrices. And the reason for using this notation is that we're going to be computing products of multiple matrices, and we need to have an ability to work with them. Because if you want 3 matrices, if I were to use this approach, I would need 12 variables. And with this approach, I only need 3 variables, the variable names for the 3 matrices. All right, and other distinctions I've known from having taught this course before, it's worth pointing out this is a set, and so a matrix is an element of this set. The matrix is not equal to the set. There is a distinction here. So this is part of the reason we invented set theory in the first place. It wasn't so that we could work with sets of numbers, it's so that we could work with sets of anything. And in this case, the set we are working with is the set of all matrices with this restriction. Okay, so now that that clarification has been made, here is the definition of multiplication of matrices. You multiply the first row of the first matrix times the first column of the second matrix. And that is the upper left corner of the product of the 2 matrices. And you see that in each of these cases. The next entry is the first row times the second column. First row of the first matrix times the second column of the second matrix, and so on and so forth. The lower left-hand corner is the second row of the first matrix times the first row of the second matrix. I might as well just put in the formula in general. A times B ij. If you might remember, it's the summation overall k goes from 1 to n. I was going to use blue here. Color coding. Because I should mention, what do I mean by multiplying a row by a column? You're taking a dot product. So in other words, you're multiplying every entry in the ith row of the first matrix times every entry in the jth row of the second matrix, term by term. So first entry times first entry, second entry times second entry, and so on, and adding them all up. And this gives you the entry in that matrix. And so this is the general formula, and you've already probably seen it in linear algebra, although we often focus on examples, and I will in a moment here as well, but we do need the general formula for what we're doing in this course. So here's my one example, the matrix 1, 2, 3, 4 times the matrix 5, 6, 7, 8. So first row times first column, 1 times 5, 2 times 7. First row times second column, I see a 1 and a 2. and a 6 and an 8. And then down here in the second row of my product matrix, I need to multiply the second row of my first matrix. So second row is 3, 4. So 3, 4 times 5, 7. And 3, 4 times 6, 8. And so 3, 4 times 5, 7 is 3 times 5 plus 4 times 7. And so this is the results. And you can compute that this is the matrix you get. So first row times first column, 1 times 5 plus 2 times 7, and so on and so forth. Now, I've mentioned before that normally when you define groups, we don't check closure, but this is one case where we have to, because, well, if you assume A and B have non-zero determinant, you need to check that A times B has non-zero determinant in order to guarantee that the product of the two matrices is still in the set. Because remember, our set is invertible matrices with non-zero determinant. So we need to check that. So let's compute this determinant of this product. Well, the diagonal terms are the product of these two numbers, A11, B11, A12, B21, and A21, B12, A22, B22, minus the product of the anti-diagonal terms. Well, math is fun, so let's FOIL it out the first term. If you FOIL out the first term, this is what you're going to get. A11, B11 times A21, B12 is this expression. To make things a little easier on myself, on each factor I group the A terms together and the B terms together. And you'll see that in each case, there's 2 terms from the matrix A and 2 terms from the matrix B. You also notice that because of this minus sign, all the terms down here are negative and all the terms up here are positive. So we assume I did this correctly, and then we look for patterns. Well, we see that these first terms actually cancel. And then we see A11, A22 is a common factor on this second column here. And A12, A21 is a common factor in this second column here. That's kind of neat. Finally, we see that these last terms also cancel. So after doing the cancellations and factoring out those common factors, we get this expression. So far, the determinant of this product of matrices factors like this. Oh, look, this is the determinant of the matrix B. B11, B22, these are the diagonal entries, and these are the anti-diagonal entries. And same here. And oh, this is a common factor in both expressions, sort of. There's one little hiccup. It has the opposite sign over here. We're subtracting off the B11, B22. But there's a way around that. You can just pull out a negative, and now you see that there's actually a common factor of B, determinant of B. And that's what we will use. And so up to this minus sign trick, we have a common factor determinant of B. What do we have left? Oh yeah, it's the determinant of A. And so, long tedious calculation, what do we discover? The determinant of the product of matrices is the product of the determinants, which is a fact we actually state in linear algebra. But now you at least see the proof in the 2x2 case. More importantly, if we're assuming that the determinant of A and B are both not 0, their product can't be 0. And therefore, the product of these two matrices has a non-zero determinant. So, in fact, like we wanted, if A and B are in GL2, so is their product. So we do actually have closure. However, it's worth pointing out that we've proven this other theorem here that might be useful in other contexts, so I will point it out. The determinant of the product is the product of the determinants. So our claim is that the set of all 2 by 2 matrices with non-zero determinant with standard matrix multiplication forms a group. What does that mean? Well, it means it satisfies the associativity axiom. There's a multiplicative identity and there are multiplicative inverses. For every 3 elements, A, B, and C in GL2R, we have associativity. Now, for the purposes of proofs, these 3 elements should be matrices. So when we do the proof, we're going to use matrices instead of lowercase letters. The next part is that you have an identity, which states that there exists an E in the set of matrices. So there's some special matrix E, which is that for all other matrices, E times G is equal to G. Finally, we have inverses, which states that for every matrix G, there is an inverse matrix, a matrix G inverse, such that when you multiply G by G inverse, you get the matrix E back again. So let's focus on the last 2 axioms. We claim there exists a special matrix, lowercase e, such that multiplication by lowercase e gives you the other matrix back. How do we find E? Well, if you did very, very well in your linear algebra course, you already know what E should be, but in this part of the video, we're going to show from first principles how to actually figure out what E is. Namely, you just take this equation and you solve. Remember here, E and G are matrices. We have a definition for matrix multiplication. This is going to turn into formulas, which we can use to solve, where E is unknown, and we're going to assume G has got known constants. In particular, keeping in mind that we're dealing with matrices, I should actually write the equation this way. Capital E is our identity matrix with respect to this group operation. And so let's write that equation out using the notation I was using. So the product of E times A is this formula. It is worth pointing out, because this looks very complicated at this point, that these A values are assumed to be constants that are known. Arbitrary but known. It is the E values that are unknowns that we're solving for. So we're looking for a formula for the E ij's in terms of the A ij's, possibly. Although obviously if there's any hope that the trick is going to work, whatever formula we're going to come up with is ultimately not going to involve the A ij's at all. Because if it did, then it would turn out that we're not going to be able to find the identity. All right, so we look at this matrix we have. This is a matrix equation now, so the upper left corner must be the same number. That gives us this equation. The upper right corner must be the same number. That gives us a second equation. The lower left corner must be the same number, and the lower right corner must be the same number. So we get a system of 4 equations involving 4 known constants and 4 unknown indeterminates. So here's our system of equations. Let's look at it for a moment. What features do you see? I see that the variables e11 and e12 only appear in the first system 2 equations, and e21, e22 only appear in the second equations. So really, you're just working with 2 separate equations. And so one way to solve this system is to work up here first. So let's try to do some elimination with the first pair of equations. Let's multiply the first equation by a12 and the second equation by a11 and take the difference between the two. And why would we do this? Because it would eliminate the constant term on the right-hand side completely, and we would see that it also eliminates this first variable. So if you do that calculation, you should see that you get a12 here, a12 here. You're subtracting them off though. I mean a11 there, the a11, a12, these terms are subtracting off. And so this is the only thing that's interesting. And you see that this middle part turns into this equation. E12, A21, A12 minus E12, A11, A22 equals 0. And that's what we get from doing elimination with the first two equations. Now remember, we're treating A21, A12, A11, A22 as known constants. And we see that we have a common factor of E12 here. Oh, and this looks like the determinant of A, or is related to the determinant of A anyhow. So if we pull out the common factor, we get E12 times negative determinant of A is equal to 0. But since A is an invertible matrix, its determinant is not 0. And so we see E12 is equal to 0. So we now have insight into our equation. We've solved one of the variables. And now we substitute 0 for E12 in the first equation. And we now have E11 times A11 is equal to A11. Well, if you divide through by A11, you get E11 must be 1. Of course, it's worth pointing out there that we're making some assumptions there. In order to divide by A11, we're assuming it's not 0. But I guess that's okay. I mean, we're working with arbitrary matrices A that have non-zero determinant. At least one of those matrices is going to have A11 as a non-zero number, and therefore this is going to work at least once. And so we see if there is an identity at all, then its upper left corner has a 1 and its upper right corner has a 0. You can play the same game with the second set of equations, namely find a linear combination that kills the right-hand side, like A22 times equation 3 minus A21 times equation 4. And if you do that and simplify, you will see that you get this expression. So what happens is that the E22 terms, these terms end up canceling when you do that calculation. And again, you end up discovering that you get a determinant times our unknown constant equals 0, so our unknown constant must be 0. And then if you substitute that in for equation 3, you end up getting that our other unknown constant must be 1. So here we're saying that the lower left corner is 0 and the lower right corner is 1. So if we put it all together and we take our original equation, we discover that the only matrix E for which this equation is going to hold for every matrix A is the case where E is 1, 0, 0, 1. Oh, that's right, we called that the identity matrix in linear algebra for a reason. But now we see where it comes from. It just happens to be the correct thing from the system of linear equations. And of course, now we wish we studied harder in linear algebra because we would have saved ourselves a lot of work by just remembering this fact to begin with. Of course, I also need to put in the disclaimer that this is not a proof yet. Remember, the goal was to find the identity element. Now that we've found it, in the next video, when we actually prove that we have an identity, we're just going to start with proving that this is the identity element. The other interesting part of proving that matrices form a group is that you have to find the inverse, which means for any matrix G, we have to find another matrix that we're calling G inverse, so that when we do the multiplication, we get the identity. As mentioned, for the purposes of this course, we're only focusing on one equality. Well, how do we find this formula? Well, of course, sometimes we memorize it, but let's suppose you don't have it memorized. Let's derive it from scratch. Again, if you don't want to derive it from scratch, you can always watch the next video instead. So what are we going to do? We're going to set up our matrix equation and solve. In particular, we're going to write AB equals E. In fact, actually here, E, as we just saw, is actually the identity matrix. And it's worth pointing out the way I have this set up. B is a known matrix that we're given, and A is an unknown matrix we're solving for. So we write down our product formula for product of two matrices. That's this left-hand side of the equation. The Aij values are unknowns to be solved for, and the Bij values are known constants. And so the goal is to find formulas for the Aij's in terms of the Bij's. On the right-hand side, we have the identity matrix. And in order for two matrices to be equal, the upper left-hand corners must be the same, the upper right corners must be the same, the lower left corners must be the same, and the lower right corners must be the same. And hence we get a system of four linear equations involving four unknowns. And let's see if there's any clever groupings this time. Well, again, like the last time, the first two equations involve the first two unknown variables, and the last two equations involve the other two. So in this case, my suggested approach is to systematically eliminate each one of the unknown variables. So first, let's eliminate A11. It appears in just these two equations. How could we eliminate it? Well, it appears that the B11 here and a B12 in the second equation. So if we multiply the first equation by B12 and subtract off B11 times the second equation, we will successfully cancel them out. So that's what we will do. And if you do that, what do you end up with? Well, you end up with B12, B21 times A12 minus B11, B22 times A12. On the right-hand side, we just have B12. And now we look for any patterns we can see. If we look at the A12, that's a common factor in both. If we look at what's left over, it looks like the determinant of B, almost. The diagonal matrix is the one that's being negated. So it looks like we have the negative of the determinant of B. So we factor out that common factor A12, and what's left inside is the negative of the determinant of B. It's equal to B12, and now we can solve for A12. It's negative B12 divided by the determinant of B. So the upper right-hand corner of the inverse is the negative of the upper right-hand corner of the original matrix divided by this determinant. It's exactly the formula we get. Next, we eliminate A12. So what combination on the first two equations will get rid of that variable? Well, if we take B22 times the first equation minus B21 times the second equation, those two terms will cancel. And that's exactly what we do. And what do we end up with? B22 times B11 times A11 minus B21 times B12 times A11. And on the right-hand side, we have B22. Again, we have a common factor of A11 here. And what's left over looks like it's exactly the determinant of B. And so we factor out the common factor of A11. We see that what's left over is the determinant of B. we divide through by the determinant of B, and we see that A11 is B22 over the determinant of B. So the upper left entry of the inverse is the lower right entry of the original matrix divided by the determinant. All right. You should note, if you haven't already, that we seem to be needing to divide by the determinant. The only reason we're able to do this is because the determinant is non-zero. If the determinant were zero, this wouldn't be possible. I leave it to you to check to see what would happen in the remaining two cases. It's a similar calculation. Try to eliminate A21. Well, how would you do that? Well, I would try, so it has a coefficient B11 here and B12 in the last equation. So I would take B12 times equation 3 minus B11 times equation 4. If you do that linear combination and solve, you will discover that A22 is equal to B11 divided by the determinant of B. So finally, if you try to eliminate A22, there's actually a mistake in that formula somewhere. Extra credit for anyone that finds it. 1 point extra credit for the first person to email me pointing out what the mistake is. But after you fix the mistake and then do the calculation, you'll discover A21 is negative B21 over the determinant of B. So if you put it all together, we took this matrix equation where we know the values of B, and we solved for A, and we found that the formulas for A were actually given by this matrix. What actually ended up happening is that the diagonal entries swapped and the anti-diagonal entries got negated. And sometimes we actually teach students this formula in linear algebra, but we just teach them to memorize it. We actually now saw through the rigorous calculation where the formula comes from by deriving it from scratch. And that's not the only way to derive it, but it's the cleanest way to derive it. And so we see this is the formula for the inverse of the matrix B. Note I'm using the standard convention where, since all the terms are multiplied by the same constant, I just factor that constant out. A natural question you might ask is the set of matrices commutative with respect to multiplication? Take some time. Think of a counterexample. Is it the case that for any two pair of matrices, AB is equal to BA? All right, after giving you at least some moment to think about it, and the ability to pause the video if you wanted to, here's a counterexample. If you multiply these two matrices together, you get a 2 in the upper left-hand corner. But if you multiply them in the other order, you get all 1s everywhere. Clearly, these aren't the same matrix. So matrix multiplication is not commutative.